Good morning, good morning, good morning, my dear lovely NEET warriors on the Vedantu NEET English channel. And today we are going to do the most important part about oscillations, SHM, that is your waves on a string and sound, light waves, and in general any wave property which is related to interference. And how the waves superimpose on each other, and the phenomena of beats, and also the phenomena of standing waves. So interference of waves, beats, and standing waves is what we are going to do, and this is applicable both for 11th as well as 12th standard portions. So let's begin with your Capto, your Captain Shreyas on the Vedantu NEET English channel, and I have been teaching kids for more than 13 years now, and I'm extremely proud and happy that many of the kids that whom I have nurtured, and thousands of them, have entered into the top-notch colleges in the country, and many of them were actually below average or just average students. So I take immense pride in that, because making a topper is not a big deal, but making an average student a good student is what I find the challenge lies, and that's where I come into the play. Okay, so thank you so much for liking the video. If you have not done that yet, quickly like this particular video and subscribe to the Vedantu NEET English channel right away, right now. Yes. And just like I have given my introduction, you too need to give your introduction if you are new to the channel. And remember, I have already given a strategy video on how to start your preparation for NEET in case you have not yet started for the last 6 months. And let me also tell you, my dear students, as you are watching this particular video, yep, you can also buy the test series as well as the flashcards for your additional preparation. Flashcards are small cards for revision. You can skip making your own notes, as well as the test series is there, which is right now going on at an all India level. You can go about it online or even offline. Remember that. Yep. All right. And all the books are also available for your additional practice. The links have been mentioned in the description box below over here. Yep. Hi, Jasmine. Hi, Mardil. TMC Capto, when will you teach fluid mechanics? I'll let you know very soon in the roar. Hi Disha, Dream TMC. Most likely a Dream TMC that will continue in the crash, because fluids is a very low weightage, and I have already done that in the the previous nurture series, right? So that's the reason for that. We'll continue in the crash. Yep. Okay. It's a low weightage topic. Let's start now. What is the meaning of interference of waves? What is the meaning of superposition of waves? And what is this beats? What is this standing waves? And what are those different formulas? Let's go one by one. Okay, so when I say interference of waves, interference of waves basically occurs when two or more waves meet at a point and then produce a net effect, which is also called as your resultant. Net effect, which is also called as your resultant. I can give you some examples. Kids talking in a classroom. Kids who are talking in a classroom. Or for the example, different lights meeting at a place. Or different ripples of water bouncing back and meeting. And there are so many more examples of interference of waves. Even you will see something called as Young's double slit experiment and so on and so forth. So there are many things. So when multiple kids in the classroom are talking, you don't hear just one sound, but you hear other person's sound, and what you hear is a new kind of sound. It's not like you can understand what one person is saying or what that person or this person is saying, but what you hear is a resultant effect. It feels like there is a noisy classroom, and if the teacher enters the classroom, they will be like, is this like a fish market or what? Isn't that right? Imagine white light is coming, yellow light is coming, green light is coming. When they all meet together, they might produce a new color, or your eye might look at it as a different or perceive it as a different color. So again, different waves are meeting together. Light is also a wave. Ripples on water, you produce some ripples. Ripples means those waves on water by dropping some stone or some particles. These ripples will go, they might hit the bank, they might come back, and they will meet each other. So these ripples meeting each other are nothing but like interference of waves. In fact, one of my first diagrams was that only. These are ripples on the surface of the water. Somebody has dropped two stones. You can see the ripples are expanding and they are meeting. So I will say that the waves are interfering with each other. Just like you say to your friend, don't interfere in my business. I am doing something. You are doing something. But what you are doing is interfering in what I am doing. Means, there is a conflict of interest, or maybe you are hampering my progress, or you are helping me, something. You are just affecting me in some or the other way. Yep. It's almost done, Chandan. Just probably this November. That's it. Good morning, Sushmita. Hi, Dhanushalia. Welcome aboard. Thank you for all the fire and hearts. And if you have forgotten to smash the like button, please do that like button, smashing that like button right now. Yes, thank you so much. Okay, so that is the meaning of interference of waves occurs when two or more waves meet at a point and then they produce a resultant effect or a net effect. And there are many, many experiments and many, many phenomena around us. You take a string and you generate a pulse. That pulse will go and meet that, and you will see interference of waves. And I can show that to you right over here in PhET. Yes, let me go to PhET and let me go to where is it? Sound and waves. Yes. Okay, let's say we go to waves on a string over here, and yep. Okay, so let's go to slow motion, and now look at this. I generate a wave. This wave is going. I know a crest will reflect back as a trough. Okay, just imagine I generate another wave together. So you saw they interfered with each other, and see now they will interfere with each other as they pass by. They are interfering with each other. Wow. Yes, so that is called as interference of waves. Let's try it one more time, but let's say we make it as a loose end and see what happens. Okay, it's really slow. Okay, let's make it normal. Okay, that wave will go. I know it is going to bounce back. Meanwhile, I will also generate one more wave from here and see what happens. They interfered and they generated a resultant wave. Now they'll again reflect back and come, and now again they have interfered. Can you see that? Yes, so that is basically called as interference. Again they are going to interfere, they are going to become big, and they are going to, yes, make a resultant effect. Yes, perfect. So that is the meaning of interference of waves. Now what happens is when the different waves interfere, the resultant is found by superimposing the effects of each wave. This is called as your superposition principle. Superposition principle. This is called as your superpositioning principle. What do I mean by that? Take the example of this only. let's say I generate a wave over here, okay, power wave going like that. Now I'll generate another wave over here, a small one. You will see that when they interfere, the resultant is combining both the waves' effects together. It feels like that small wave was going on that big wave. Both of them are producing their effects all together. They all retain their effects and they produce the resultant one. Look at this now again over here. This is a big trough and a small crest. You should see a small trough over here. You can see what happens when they interfere. It's a small trough at just that instant. Just visualize that. And now again, when they go and meet back over here, you will see it will be a big trough. Small trough, big trough will make it a big trough. Both of them give in their effects and they create a big trough, and you can see that. So that is what is the meaning of superpositioning. The resultant is found by superpositioning all their effects together to see what the net resultant is. That is called as the superpositioning principle. Got it? Hi Madhumati, hi Phoenix. Yep. Sarani, I hope you understood. All right, great. It's a really wow thing, trust me, yes, to see and hear about superpositioning and interference. Okay, so to write it mathematically, the resultant effect at any point, at any instant is given by the wave number 1's effect at that same location at that instant plus the wave number 2's effect at that location x at that time, and so on and so forth. There could be n number of waves. So the nth wave's effect at that location at that time. That's how you read this. You will see this equation in many books. Don't get scared by looking at this equation. Sir, what the hell is this? What is y? Y is the effect. Y is the coordinate. How much it went up or how much it went down. That is the effect of each wave. So each wave will give an effect at that location, at that instant. So you will add all of them together to get the resultant wave. Wow, this is cool, sir. So how do I exactly solve these kind of equations, sir? Do we have complex equations, sir? The answer for that is no. We have very laddu, simple equations. Even in JEE Advanced, you don't get such complex equations. You have simple equations of sine and cos. Okay. Now, if you remember, a quick recap of our wave equation, of our wave equations, how does it look like? Of our wave equations, how does it look like? If you have a wave which is going like this, it looks something like this. Y as a function of x and time is nothing but a. You can use sine or cos, doesn't matter. Sine, you have kx plus or minus omega t, right? This is how you have it, right? You can also have some phi over here, which is the phase constant. That is how your wave equation generally looks like, right? Okay, yes, we will be doing PYQ series after this, definitely, don't worry about it. That is how your general wave equation looks like. Now, my dear students, just one second. Now imagine you have two or more waves, or let's say for example, two different waves, okay, interfering at a point, meaning something like this. Just imagine this. There is a wave like this which is going to come over here, and there is, let's say, another wave over here. This is the point at which they are going to meet, and after this point, what is going to happen is you're going to see that these two waves these two waves after this point, when they meet, you will see that they might produce a new kind of wave. They might produce a new kind of wave which will go over here. So this is basically your resultant wave. This is basically your resultant wave. This is your wave number 1. This is basically your wave number 2. Two people are talking, their waves will meet and the resultant wave will enter your ear. Two or more stones are thrown in water, those ripples will meet and then they will produce a resultant. So that is what the meaning of this is. Two torches or two light sources generate light waves, their light waves meet and they produce a resultant light wave. That is the meaning of this particular diagram. So when two or more waves interfere at a point, here I have taken the example of two waves for simplicity, they will produce a resultant wave on this. It could be a string also. Now, how will this resultant wave look like? That is the main question. Let's say the wave number 1 has an equation given by A1 sine kx plus or minus omega t, and then you have, let's say, phi 1. Then you have y2, which is basically A2, and this is sine kx, A2 sine, okay, you have kx plus or minus omega t plus phi 2. Now, very important to see what we notice over here, the k's are same, omegas are same. That means the wavelength is same, the frequency is same. You'll be like, sir, what will happen if the wavelength and the frequencies are not same? That kind of studies we do not have in NEET or even in JEE syllabus. None of the 12th standard books or none of the 12th standard coaching or none of the 12th standard exams have multiple frequencies, multiple wavelength kind of questions. That is an advanced topic completely altogether. Okay, so we study the interference of those waves of basically same frequency and wavelength. Very, very important. Wavelength. Yes. Same frequency, which means their omegas will be same. Wavelength is same. That means K will also be same. Yes. That is what we study in our NEET or any competitive exam syllabus. Keep that in mind. Okay. I hope this is clear. Now, why is this phi different for both of them? That means, see, phi tells me the situation, the state, the condition. Like what condition am I in? I am bored, I am interesting, I am very happy. So the waves also have a condition, means what situation they are in. So where are they? What are they doing? I can sense it right now that this wave is slightly late as compared to this wave. These are like two friends. This friend reaches here first. This friend has some more distance to cover over here to reach this particular place. So that is why their phases are different. That means their situations, their conditions are also different. Is this understood? Give me a thumbs up. Why phi is different? Hi, Ethereal Dream. Yep. Everybody understood it till this point? Their phases, their condition, their situations are different because this guy is late, this guy is early. You call a friend, hey, let's meet at this coffee shop. The coffee is very good. Your friend reaches very early and you are late. So yes, phi is different, situation is different, the condition is different. Now, that phase difference, right? That phase difference. So the phase difference between the waves delta phi is nothing but phi 2 minus phi 1, modulus of it. Usually you take the mod value, you do not take minus 30 or minus 40 degrees. Even if it is negative 30, you always take the positive mod value, which is plus 30 degrees or plus 40 degrees. So phase difference is usually a positive number. That's how we usually associate it with. How much is this phase difference, you might ask? Well, don't have to worry about it. It's very straightforward. I'll tell you what you can do. In order to find how much this particular phase difference is. all you need is this particular thing. This has to cover this much distance. This has to cover only this much distance. If this is x1, if this is x2, this is the path which this wave has to cover. This is the path which this wave has to cover. So there is something called as path difference. Something called as the path difference. This is called as the path difference. That is delta x, which is again x1 minus x2's modulus, which is how much different these paths are. I have to travel 3 kilometers. My friend has to go only 1 kilometer to reach the coffee shop. So I have to travel 3. My friend has to travel 1. Anyways, both have to cover that 1 kilometer. The extra length that I have to cover is 2 kilometers. 3 minus 1 is 2. So that is the difference in the path that will cause the delay in the arrival. So when my friend would cover that 1 kilometer, I still will have to cover that 2 kilometers to reach that coffee shop. So that is the meaning of the word path difference. How different are your path lengths? So that will cause the delay in the arrival at the meeting point. Now, obviously, the phase difference will be related to the path difference, and we have seen the formula in the previous lecture. If you remember, a 2 pi radian of phase relates to a length of a wavelength. A 2 pi radian, let me remind you, 2 pi radian of phase relates to one wavelength. Yes, a wavelength. Yes, one particular wave. So if you have a length of delta x, it relates to delta phi. So obviously now we got the idea. Delta phi by delta x. Delta phi by delta x, radian per meter, will be equal to 2 pi radians per wavelength. So delta phi radian, meter, radian per meter. That is the relationship. So in general, I can then say that the phase difference is nothing but 2 pi by lambda into basically delta x. So that is the formula, my dear warriors. That is the formula. Is that clear, my dear students? If I know the path difference, I can find the phase difference. If I know the phase difference, I can find the path difference. That's the relationship between that. Great. Welcome, objects in the mirror. I think your name is convex mirror. Okay. So we have till now seen, okay, what is interference, which is meeting of waves. And when the waves interfere, they obey superposition to produce a resultant effect. A general wave equation which we simply study is sine or cosine waves looking like this. And when they meet, they will have some phase differences between them because they might not arrive at the same time. And because they have some phase difference, that can be calculated by their difference in their path lengths that they have to travel to arrive at the meeting place, which is called the path difference, and that is related to the phase difference, which is further going to help me to calculate how much is the resultant wave. We are going to come to that. Hold on. Okay. Now, the next important thing. Now, all I'm interested is figuring out what is that resultant wave equation going to look like. I know this guy's equation looks like this. Y2's equation looks like this. What is the resultant wave going to look like? You'll be like, sir, just add these two. Yeah, that's it. Fine. I know. I agree with it. So YR is simply put, it is nothing but Y1 plus Y2. But you know what? It is not as easy as it looks, because when I try to find the resultant, each one of them, this is nothing but a1, then this is sine, then this is kx, then this is plus minus, then this is omega t, then this is phi 1, and then I again put a plus over here, and then I will put a2, and then I will put sine, and then I will put kx, and then I'll put plus minus, then omega t, and plus phi 2. How do I exactly solve them? How do I exactly solve them? Because you know, they are two different sine terms and all of that. Can I combine it as one single term is the big question over here. Can I write it down as one single term is the question over here. For that, I will want your attention on this particular thing. Let's go to Desmos. Yep, let's go to Desmos. Let us start writing down some wave equations over here. Observe it carefully. Yep, y is equal to, let's say I will just choose one equation, something like 5, or maybe I'll just choose this as a, and then I'll just sine something like omega 1 and then x. Okay, right, omega 1 and x, right, cool. This is one equation. Then here a and omega can be varied, all right, and let's say omega can go between 0 to maybe 100 in the steps of, let's say, 1, and amplitude again, let's say 0 to 10, and maybe in the steps of 0.1. Okay, then similarly, now this was just, let's say, y1. Similarly, let's say y2 is equal to, this was a1. Okay, just 1 second, guys, it will take some time, but yes, 0, this is 10, 0, this is 10, this is 0.1. Okay, perfect. So now next, this is, let's say, a, this is some another amplitude a2, and let's just choose this function sine of something omega 2, and let's say x. Where is it? X. Okay, perfect, done, dusted. Okay, omega 2 is going to be the same as omega 1. All right, enter. Okay, this is done, because the frequencies have to be the same. And amplitude 0 to 10, let's say step of 0.1 over here. Okay, perfect, done, dusted. Now let me show you what these waves are. Look at this. This is your first wave, the red one. As you can see, I can change the amplitude, I can also change the frequency. Okay, I can change the wavelength, anything. Okay, just showing you some random thing over here. That's 100, that's too much, I think 10 is enough in the steps of 0.1. Okay, okay, now that was basically your wave number 1. Now let me show you wave number 2. This is your wave number 2. As you can see, I can change the frequency, I can also change the amplitude of this wave. Now let me show both the waves together. I hope you can see both these waves together. Wave number 2's amplitude I am able to change, the purple one, okay, and the red one is basically the first wave. As you can see, I can change the amplitude of that, and together I can change their wavelength or their frequency. But right now, do you see they are both in sync? Crest, crest, trough, trough, crest, crest, trough, trough. They are in sync. That means, is there any kind of phase difference between them? 100% no. There is no phase difference between them. So let's introduce that, and for that I will add that phase difference, And let's say the phase difference over here, I'll just put it as PHI, which is your phi. And let me add a slider for that. And this can go between 0 and of course pi, that is 180 degrees in the steps of pi divided by, let's say, 20. Okay, right now 0 phase difference. As you can see, I can shift the phase difference like this. I'll just make it 2 pi if needed. See this, 0. I am changing the phase difference. Do you see the wave is shifting? The other wave is shifting relative to the first wave. So the path difference is being created, or basically a phase difference is being created. Everybody with me, my dear students, can you see that very, very clearly? As I change this phase difference, yes, if it is 0, they align perfectly. See what happens if I make it as pi radian. If I make it as pi radian, crest with trough, trough with crest, crest with trough, trough with crest. Are you able to see that? Now it means that they are out of phase, they are out of sync, they are opposing each other. Yep, I hope you can see that very clearly. See how the crest with trough, trough with crest, definitely they are out of phase, they are not in phase. In phase will be if the phase difference is 0 or even 2 pi. 2 pi means one complete rotation. So it's back to 0. So then they are perfectly aligned. This is said to be in phase, whereas this is also in phase. Yeah, this one over here is said to be out of phase. Is this absolutely clear in your head? Let me know. Is this absolutely clear in your head? What we are trying to represent, what we are trying to do over here. I'm trying to make a visual interpretation. I'm trying to make you visualize everything. I'm making you feel this particular physics part. No teacher will do that. Trust me, they will just keep writing on the board, blah, 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 blah. No, we are not going to do that. We'll make sure that the concept enters your head. Okay, great. Perfecto. Now, it's obvious that the resultant, which is combining both these waves, will depend on everything, amplitudes, obviously the phases and everything else. So if, now observe this carefully, I will write the resultant wave. This is y resultant, this is y resultant, y, let's say r, oops, I can't write y r, I'll just write it as y, is equal to, I'll just write it as y1 plus y2. Very interesting, guys. This is going to be crazily interesting. Look at this. I will have to change the color of that. How the hell do I change the color? The green one. Perfect. Done. Okay. Now look at this, guys. The green one is the resultant wave. The green one is basically the resultant wave, and I want you to pay full attention on how the resultant looks like. Observe it carefully. Observe it carefully how the resultant looks like, guys. Observe it carefully. Okay. See, wave number 1 is red, wave number 2 is the violet one, and the green one is basically the resultant wave. Right now, when the crest meets, crest trough meets, can you see the resultant is really huge? Obviously, their peaks and their valleys are meeting together. Very good kind of interference. For example, I make the first wave's amplitude as 1 and let's say the second wave's amplitude as, let's say, 2. Okay, then amplitude 1 is 1, amplitude 2 is 2. 1 plus 2 will give it 3. If I make the amplitude 1 as, let's say for example 3, and the amplitude of the wave number 2 is 2, 3 plus 2 should give me 5. exactly. Can you see the amplitude of wave number resultant is 5? This is 2, this is 3. 2 plus 3 is 5. 2 plus 3 is 5 on either side. So, what's happening to the amplitude? The amplitude is just an addition of this amplitude and this amplitude together, provided they are in sync, they are in phase, they are together. Their phase difference is how much? 0 radian, 0 degrees. But I think things will change drastically the moment I change this. Oh, look at that. I have created some phase difference. There is some difference in the phase. The amplitude is no longer 5. It has changed. I think the moment I make it out of phase, meaning the phase difference is pi radian. Pi radian is 3.14, right? Pi is 3.14. Do you see? Crest amplitude 1 is 3. Amplitude number 2 is 2. 3 plus 2, 5. No. 3 minus 2 is 1. Because notice the red, which is the first wave, has an amplitude of 3. At the same time, the second wave, which is the purple one, has an amplitude of 2. So that 3 and this 2, which are opposite, produces a resultant of the remaining 3 minus 2, which is just 1. That is the least resultant. The green one is the resultant that you can ever get. That's the least resultant that you can ever get. Notice, no matter what I do, I will never be able to go below 1. Below 1. That is the least amplitude. This is the maximum amplitude. And that's about it. No matter what I do. Do you see that, my dear students? No matter what phase difference I choose, maximum amplitude is 5 of the resultant, the least amplitude is 1, and again the amplitude starts growing to 5. And the least amplitude is when they are opposing each other, that is when the phase difference is pi radian, and the maximum amplitude is when they are in sync, that is 0 radian or 2 pi radian. Now that gives me an idea of how we should be combining waves. Something similar we studied in one of the first few chapters of the physics. Can you remember the chapter? Well, if you can't, I'll give you a hint. The chapter of vectors. The resultant vector is maximum when the two vectors being added are in the same direction. The angle between the two vectors is 0 degree. The resultant vector is the least when the vectors are in the opposite direction, that is 180 degrees. Then the resultant is the least. If the vectors are at any other angle, then the resultant will be lesser than the maximum, but more than the minimum. This is sounding very much similar to what is happening over here. Just that here you don't have vectors, but you can make a forceful vector over here. That forced vector is called as a phasor. That forced vector over here, which is not actually a vector, but you make it sound like a vector, make use of the vector properties, you dress it up like a vector. It's not a vector, so that is basically called as a phasor. So my dear warriors, now we are going to make use of something called as phasors, and you will see what the resultant will be. Over here, I saw one thing very clearly. That when the phase difference was 0 and I said they are in phase, then this particular wave and this particular wave, when added together, what it gave me a larger wave. What it gave me is a larger wave of amplitude A1 plus A2. This was having amplitude A1, this was having amplitude A2. This kind of thing which just happened is also called constructive interference. Constructive interference. Constructive interference. Yes, this is called constructive interference. It's like thinking of a vector whose amplitude is A1, another vector whose amplitude whose length is basically A2. The amplitude becomes the length of the vector. The resultant vector is just the sum of both of them. So it is A1 plus A2. This is the resultant. This is the resultant of these two vectors. Amazing. This is called constructive interference. Crest with crest, trough with trough produces a larger crest and a larger trough, which is exactly what we saw over here for zero phase difference. A1 plus A2 is the resultant amplitude. That was constructive interference. Similarly, you will also see that you will get when delta phi is basically pi radian, just like here it was 0. This is said to be out of phase. This is said to be out of phase, meaning you will have a wave like this of amplitude 1. You are adding it with another wave of amplitude A2, and together they will produce a resultant. This is a big trough, small crest. So small trough, small crest, something like this. Amplitude will be A1 minus A2, modulus of it, whichever is bigger. Okay, this is what you are going to get. So this kind of interference is definitely now called as destructive, because they destroy each other. Destructive interference. Okay, destructive interference. So you will see over here that a first wave might have amplitude A1, so you will treat it like a vector of length A1. The second vector has an amplitude of A2. You will treat it like a vector of length A2, and the resultant will be this much. This is the resultant. This is the resultant whose length is whichever is bigger minus whichever is smaller, the modulus of it. So you will always take the positive difference. Don't write it as A1 minus A2 always. It could be A2 minus A1. So that's why we put modulus, whatever is the remaining length. I hope this is absolutely clear. Now you might be wondering, will phase difference of pi radian only do? Will something else also be okay with it? Will only 0 radian work for in phase? The answer is no. In fact, what you will see is that your delta phi can be 0, it can be 2 pi, it can be 4 pi, it can be basically 6 pi, basically any even times of pi will do. Why? Because 0 degree is, or 0 radian is here. Pi by 2, pi, 3 pi by 2, 2 pi. So 2 pi is in the same direction as 0. So that's why 0 and 2 pi is the same thing. So 0, pi, 2 pi, 3 pi, 4 pi. 4 pi is again the same thing. 5 pi, again 6 pi. 6 pi is the same thing. 7 pi, 8 pi. So every even pi, you will see it is pointing in the same direction. So it's as if saying 0 degrees. So that's why 0, 2 pi, 4 pi, any even pi will do. Is that absolutely clear? Same thing over here, my dear students. Will delta phi always be pi radian? Not necessarily. Okay. See, this is 0, this is pi by 2, this is pi radian with reference to this 0, that is pi radian. So think about it. 0, pi, 2 pi, 3 pi. 3 pi is same as pi. 4 pi, 5 pi, 5 pi, 3 pi, pi, same thing. Again 7 pi, again 9 pi, 9 pi, 5 pi, 3 pi, pi, all are in the same direction, so there is no difference at all. So delta phi can be pi, can be 3 pi, can be 5 pi, can be 7 pi. Basically any odd multiples of pi radian will do for the phase difference, for it to be out of phase. I hope this is absolutely clear. Now, what about the part difference? If you remember, part difference and phase difference were related to each other. Yes, so imagine if this is 2 pi, 2 pi, 2 pi cancels, what will delta x be? what is the possible values of delta x. Let's try to see what are the possible values of delta x. Just for your reference, I am writing the value of delta x will be nothing but lambda by 2 pi into delta phi. That is the formula. Okay, because delta phi was 2 pi by lambda into delta x. So delta x will be lambda by 2 pi into delta phi. Think about it. Delta phi is 0. 0 into anything is 0. So yes, I will get this as 0. Delta phi is 2 pi. 2 pi cancels. What I will get? Lambda. Okay. Delta phi is 4 pi. 4 pi by 2 pi? 2. 2 into lambda. So this will be basically 2 lambda. Next, this will be 6 pi. 6 by 2, 3. So 3 lambda. Then 4 lambda. Basically, any n times of lambda when the phase difference is any n times, 5 lambda, 3 lambda, 2 lambda, 100 lambda, 1000 lambda, 1 lakh lambda, 2025 lambda, 178 lambda, or 265 lambda, doesn't matter. Whenever the path difference is any n times of lambda, it will be a constructive interference. It will be a constructive interference. Here, let's try to think. Let's try to think what the path difference possible values are. Let's try to recollect what is delta x. It is nothing but, lambda divided by 2 pi into delta phi. Substitute the value of delta phi as pi. Pi by 1 by 2. That means lambda by 2. Okay, lambda by 2. Okay. Next, it is 3 pi. 3 pi by 2. So pi cancels 3 by 2. So 3 times lambda by 2. Okay. Next, put it as 5 pi. Pi goes 5 by 2. So that will be 5 times lambda by 2. So next will be 7. Next will be 9. So 1, 3, 5. All odd numbers, guys. So odd times lambda by 2. Half of the wavelengths, odd multiples. Half the wavelengths, odd multiples. Lambda by 2 is 0.5. 3 by 2 is 1.5. 5 by 2 is 2.5. Basically 0.5 lambda, 1.5 lambda, 2.5 lambda, 3.5 lambda. So between 3 and 4, there is that 3.5. Between 4 and 5, there is 3.5. So for 1, 2, 3, 4, 5, 6 lambdas, you will get constructive interference. For 0.5, 1.5, 2.5, 3.5, 4.5 lambda, you will get destructive interference, basically out of phase. Is this absolutely entering your head? Let me know in the chat box. I have done everything. I'm doing everything step by step in detail so that you never get confused. All these theory notes will be given to you in the treasure box, guys. Yes, there will be a PDF which will be sent to you in the treasure box. The link for the treasure box is there down in the description box below over here. Yep. Great. So that is what your delta x and delta phi will be for destructive as well as for constructive interference. Destructive also we have seen over here. If I make the delta phi as, let's say, pi radian. Yeah, this is pi radian. This is destructive interference. You might be wondering, sir, what if the second amplitude is also the same? Look at what the resultant happens. Do you see what is happening to the resultant, guys? Just see what is happening to the resultant. It is one flat line. Did you see that? Did you see that? The resultant is basically a flat line. Only when the amplitudes are different, the resultant is having some value. Otherwise, it will be flat. This is a perfect destructive interference. I mean, the crest perfectly cancels the trough perfectly cancels the crest. That's a perfect destructive interference. That's a very good kind of destructive interference. But usually our delta phi may not be these values or even these values. So what to do in that case? What is the resultant wave's amplitude? The resultant wave's amplitude looks something like this: sine kx plus minus omega t. You will have obviously a new phi of the resultant. What is this AR? What is this resultant amplitude going to be? Well, for that, here I write it down. If delta phi in general, it is neither constructive nor destructive, such a thing is called as intermediate interference. Intermediate interference. It is neither constructive, it is neither destructive. That is called as intermediate interference. Obviously, delta phi is related to delta x like this. And in such cases, what you do, if this is wave number 1, amplitude 1, added to maybe wave number 2, amplitude A2, producing a resultant of something else only. This is the resultant having an amplitude of AR. What you do is you show the first amplitude as a vector whose length is basically A1. The second vector whose length is amplitude A2, but show it at an angle, which exactly equals to this delta phi. So the phase difference becomes the angle between the two vectors. The phase difference becomes the angle between the two vectors, and then using triangle law, just complete the third side. That becomes your resultant. Notice how when it was constructive interference, delta phi was 0, so you could simply add them, and when delta phi was 180, that means they were opposite, you could still just subtract them. But when it is making some random angle, it could be 30, 40, 50, any degrees or radians, then you just use triangle law of vector addition. So basically what we have done, I'll just summarize it right over here. The waves are superimposed by considering something called as phasors, whose lengths are amplitudes, whose lengths are basically amplitudes, and direction, and the direction is decided by the phase. Direction is decided by the phase and are treated like vectors, The resultant wave's amplitude, is found by vector addition of these phasors. Vector addition of these phasors. Vector addition of these phasors is found by the vector addition of these phasors, where the angle between them is phase difference. Angle between them is basically the phase difference. So therefore, I can also say AR is nothing but root of A1 square plus A2 square plus 2A1 A2 cos del phi, phase difference, because we know AR vector is equal to A1 vector plus A2 vector. You are using vector addition of the phasors. Phasors are forced vectors. They are dressed up like vectors. They are not actual vectors, but you're making use of the properties because it simplifies the analysis, and that's how you find them out. So very, very important, guys. All these things in general. Is this okay? This is for constructive. This is for, sorry, that was for in general, intermediate. This is for destructive. This is for constructive. Okay. Great. Now there is one more small formula over here, which I will derive it on the next slide. If you remember, energy of a wave was directly proportional to the square of the amplitude. Remember, energy, power, or intensity, all these things, energy, power, intensity of a wave is always directly proportional to the square of the amplitude, to the amplitude's square. We have seen this in the previous lecture of waves. If you remember those formulas, you can just go back. You can just go back to the lecture or the notes. You will see that over there. So if I write a formula for energy or power or intensity, it doesn't matter. Can I just say that, let's say for example power, or let's say even intensity, it doesn't matter. Intensity being proportional to the amplitude square, I can just say intensity is basically k times of a square. How will the resultant wave's energy or intensity or power look like? Here is the thing. Observe this carefully. Whatever equation I got over here, I'll just square it. So now we know that the resultant amplitude square is nothing but a1 square plus a2 square plus 2 times a1 a2 cos del phi. This is what we know from before. This is just from the last slide. There I had put the root. I have just squared it on both sides. Now what I will do is, observe carefully, I will just multiply this entire equation with, some k. K is some constant. You might be wondering, what the hell is this k, sir? This is some constant. This is some constant of proportionality. So I'll multiply this with k. I'll just multiply this with k and see now what exactly happens. Observe this carefully. So here we have, of course, a1 square. Here we have a2 square, here we have 2, here we have a1, we have a2, and we have cos del phi. Observe carefully. This is k, this is k. Well. I am not getting k 2 times over here, so maybe I will need root k over here so that I can split it like this. Now what is k times ar square? Just k into amplitude square is intensity. So k times ar square will give me resultant wave's intensity. This is resultant wave's intensity. K times a1 square will be intensity of wave number 1. So this will be I1. This into this will be just I1. Similarly, what will be k into a2 square? K into a2 square will be intensity of wave number 2. Now here is the problem. What do I do over here? Don't worry. I'll do one thing, one small change. I'll put a root and then square. Now k into a1 square. K into a1 square is nothing but intensity of wave number 1. K into a2 square will be intensity of wave number 2. So this is root I1, this is root I2, and this is basically cos del phi. Oh, so this is the resultant intensity formula. Similarly, you can also use it for power or energy. Similarly, you can also use it for power or even energy. So you can say power of the resultant wave or energy of the resultant SHM. simple harmonic motion, oscillation, power of a wave on a string, intensity of light or sound, everything has similar things. So it will be P1 plus P2 plus 2 times root I1, I2, and cos delta phi is outside. Similarly, energy of the resultant SHM will be energy of SHM1 plus energy of SHM2 plus 2 times root E1, E2, and then you have cos delta phi. Addition of waves, addition of SHMs, superposition of SHMs, all have the same theory. It is nothing different. Is this absolutely clear how this formula works? So any of these formulas, guys, you can remember it's one and the same thing. So I'll just block this for now because other three, all the three are the same things only. Clear? Everyone till this point? Hi Parishad, welcome. Clear, Mardai, super Ravi, awesome Disha, very good Kaveri, 𝐿𝐿𝐵, loving it, Disha, loving it, error analyzer, loving it, great, awesome guys, awesome. Thank you Soni Mohan for all the love. Okay, now if I ask you, what could be the maximum resultant intensity? What could be the maximum resultant intensity? That will happen here. When the wave becomes very big, maximum resultant amplitude, maximum intensity is possible in constructive interference. So going over here, when there is constructive interference, we know that the intensity of the resultant wave will be maximum, and we can find that I max of that particular resultant wave like this. It will be I1 plus I2 plus 2 times root I1 I2. Here you will have cos 0 because it is in phase. Yes, it is constructive. Cos 0 is 1. Okay. So what to do now? Shall I leave it like that? Answer is no. I have an idea. Why not write it like this? Root I1 square is the same as I1. Putting a square with the root is the same thing. Okay. I2, I will write it as root I2's square. I know you are wondering, sir, why the hell are you doing that? I mean, you could have written cube also, sir. But why the hell are you writing root? Because I can see a root here. That's the reason why I'm writing root. But sir, why are you crazy? Why are you writing this root? What are you going to get from this? Hold on, I will show you. Now this is 2 root I1 and this is root I2. Cos 0 obviously is nothing but the number 1. I'll be like, what is this, sir? What have you achieved? I remember one identity. This is A, this is B. A square plus B square plus 2AB. A is root I1, B is root I2. So 2AB, this is A square and this is B square. Oh, now I understand, sir. You are very smart, sir. I understood it, what you just did. So this is I max of the resultant is maximum when they are in phase constructive interference, and I get this. This is A square, this is B square plus 2AB. So that is nothing but A plus B whole square, correct? So that is it. So that will be root I1 plus root I2 and the whole square. That is the maximum intensity which one can achieve. Is this absolutely clear? That's the maximum intensity which one can achieve. Yes, thank you for reminding me to hydrate. Awesomeness. Very good. So, when do you think this intensity would be minimum? When do you think this intensity would be minimum? Well, let's come back. It will be minimum over here. Over here, when it is basically destructive interference. When it is basically destructive interference, that's when the intensity will be minimum. Okay, let's find out that minimum intensity. I minimum of that particular resultant will be basically you have I1 plus I2 plus 2 root I1 I2. Here it will be cos pi, and cos of 180 is -1. So this will be nothing but I1 plus I2 minus 2 root I1 I2. Whatever trick I use there, I will use it here also. I'll write it as root I1 square. I'll write it as root I2 square, and see now how the magic happens. So the minimum intensity of the resultant wave will be, this is A square, this is B square minus 2AB. So this will be A, which is root I1, minus B, which is root I2, and the whole square. So this is the least intensity of the resultant wave, root I1 minus root I2. Is this clear, my dear warriors? Everyone with me? Root I1 minus root I2. This is minimum intensity. This is the maximum intensity. So we have done the theory for the interference of waves. Yep, we have done the theory for the interference of waves, including in general interference. Let's do some basic questions before we move on to standing waves and beats. Okay, let's do some basic questions. We will have a separate problem solving session, of course. If waves of amplitude 2 meters and 4 meters have a wavelength of let's say 10 meters and a phase difference and a path difference of 5 meters. Find the phase difference and the amplitude of the resultant wave. That's the question. Let's try to solve this, not that difficult. Lambda is given, path difference is given, phase difference is asked. Phase difference, the formula becomes 2 pi by lambda into delta x. Well, the wavelength is already given to be 10 meters. The path difference is already given to be 5. So 5 by 10, well, 5 by 10 is nothing but that 1 by 2, 2 cancels, so it will just become pi radians. So the phase difference is basically pi radians. 100% now this is a destructive interference. This is nothing but a destructive interference. The moment it is destructive interference, I know that the resultant wave's amplitude will be just A1 minus A2 modulus. Hence the correct answer for this will be nothing but 4 minus 2's modulus, which is just 2. So the resultant wave's amplitude is 2 meters. Everyone with me on this? Shall we go ahead? Yep, the difference of the amplitudes will be what it is. Moving on to the next question, guys, coming up on your screen. Moving on to the next question. Here it is. If waves of amplitude 3 meters and 4 meters interfere by a phase difference of 90 degrees, find their resultant. Find their resultant's amplitude. Find their resultant's amplitude. Come on, my dear students. What do you think the correct answer for this should be? You have two waves of amplitude 3 meters and 4 meters, and they interfere by 90 degrees phase difference. Meaning, construct a triangle now. Simple. See, there is one wave of amplitude 3 meters, another wave of amplitude 4 meters, and clearly it is mentioned the phase difference between them is 90 degrees. So obviously this would be their resultant. This would be the resultant. Oh, I know what it should be now. Use Pythagoras. It will be 3 square plus 4 square, which is the root of 25, which is just 5 meters. So the resultant wave has an amplitude of just 5 meters. Clear, everyone? Awesome. Moving on to the next question coming up on your screen. Moving on to the next question coming up on your screen. If two waves have intensities of maybe, I don't know, 3 watt per meter square and 1 watt per meter square, the maximum by minimum ratio of resultant intensities of their resultants intensities is how much? Intensities is how much? See, there are two waves. One has an intensity of 3, another has an intensity of 1. Or else I can choose something else. Let's say 4 and 1. Okay, 4 and 1. And the question is, what is their ratio of their maximum and minimum resultants intensities? So if they interfere and they produce maximum intensity, if they produce basically maximum intensity, I know that will happen for constructive interference. That will happen for constructive interference. And when they produce minimum intensity, that will happen for destructive interference. The maximum intensity that you can get, we have already seen the formula. It is root I1 plus root I2 the square. And the resultant intensity's minimum value is root I1 minus root I2 the square. 1 second, guys. Just 1 second. All right, let's have a look. So this will be root of 4 plus root of 1 the square. Root of 4 is 2, root of 1 is 1, the square. 2 plus 1 is 3, 3 square is 9. Here this one is root of 4 minus root of 1 the square. Root of 4 is 2, root of 1 is 1 square. 2 minus 1 is 1, 1 square is 1. So hence I will get my final answer. The maximum upon the minimum intensity value will be 9:1. That is the answer. 9:1. Everyone with me? 9:1. Everyone with me? Crystal clear? Everyone? So this is how you solve these kind of questions. Let's solve another question coming up on your screen. Here it is. Two waves of power 4 watts and 2 watts having a path difference of 3 meters for a wavelength of 12 meters produce resultant power of dash watts. That is the question. Read this question again. There are two waves of different powers and different, you can say they have a path difference of 3 meters. The wavelength is 12 meters. What is the basically resultant wave's power? That is the question. Can you figure this out? Come on, let's try this. I think to solve this question, because path difference is given, we need to do the first calculation of phase difference. So let's do the calculation of phase difference, which is nothing but 2 pi divided by lambda into basically delta x. So 2 pi, wavelength is basically 12, path difference is basically 3, 3 by 12 is 4, so 2 pi by 4, which is basically pi by 2. Okay, so delta phi is basically pi by 2. What next? Think. What next? Think, guys. Once you know the phase difference, use the intensity formula. What is the intensity formula? The power formula of the resultant. The power formula of the resultant is P1 plus P2 plus 2 times root P1 P2 cos del phi. Okay. So what is power number 1? It is 4. What is power number 2? That is 2 plus 2 root 4 into 2 cos of pi by 2. Cos 90 is 0. So 4 plus 2 is just 6. So 6 watts. So the resultant power is just going to be 6 watts. That's the answer. Is that right? So I hope you guys got a hang of how to solve this interference problems in general of constructive, destructive, or even general, and how energy calculations are also done. So these are the main theory points. These are the main theory points. Till here, I hope everything is clear. I hope everything is clear till this point. Okay. Now let's go to the second interesting phenomenon of interference, and that is called as beats. That is called as beats. Now what the hell is beats? When you hear the word beats, you think of some discotheque or some DJ and or some nice music. So the beats of this is very nice. Yes, that is in different context. But here when we talk about beats, what I mean is you have very similar looking waves, sound or light, or in general any kind of waves, and they look very similar. If you hear them differently, you're like, this is the same sound. But when they are played, sounded together, then you note the difference, and slowly there is a sudden increase in the sound, and then there is a sudden decrease in the sound, and you will see the sound increasing, decreasing, and that is what is called as beats. So beats in sound is basically when similar waves interfere with each other, they produce alternate constructive, that is also maximum sound, or also called as sometimes waxing, and destructive, meaning minimum sound, sometimes also called as waning sound. Okay, that is basically called as beats. That phenomena is basically called as beats. That phenomena is basically called as beats. Okay. So what do I mean by this? Observe carefully. Look at this. We are talking about beats over here. There is a wave. Like this. It has a frequency of omega 1. There is another wave like this. It has very similar looking characteristics, but there is a small difference between the two. The frequency is omega 2. When you add both of them, they are waves of similar frequencies, not exactly same, but they look very, very identical. What you get as a resultant is something like this. Oops, sorry. Like this. Maxima, minima, maxima, minima, maxima. Loud, no sound. Loud, no sound. Loud, no sound. This is like constructive, destructive, constructive, destructive, constructive, destructive. Waxing, waning, waxing, waning, waxing, waning. This resultant is basically called as beats. So the resultant amplitude is 2A, if you see right over here. Okay. And here the amplitude is nothing. So this is basically your alternate phenomena. So this is constructive. This is again constructive. This is also called waxing. This is also called waxing. Okay. Constructive, you can also call it as maxima or maximum sound. And every other in between is basically your destructive, which is minima. This is again destructive, again minima. This is also waning, waning of sound. Okay, this is also called waning of sound. That is what happens. This is called as the phenomena of beats. I will show that to you again using the calculator. It is very, very easy. Okay, so let me use a new blank graph. Okay, so let's create a wave. Y is equal to maybe something like 2. Okay, y1 is equal to, let's say 2, and then we have sine, and let's say we choose something like omega 1 and x. Okay, great. And now this is omega 1, and let's say anywhere between 0 and let's say 10.1. Okay, perfect. Next, y2 is equal to, let's say 2, again let's say sine, and omega 2 and then x, and this omega 2 again, oops, what just happened? Anywhere between 0 and 10 with the steps of 0.1. Okay, perfect. Now look at this carefully. Let's choose something like this, 5. Okay. Not needed. Okay. Now observe carefully. One wave is 2 sine 5.1x, other wave is 2 sine 5x. 5.1 and 5, the frequencies are not that different. I'm not sure, Sanwala Sheikh, I think you should be eligible for a very good amount of scholarship for sure. Okay. But you will get a call. Everything will be discussed with you by the counselor on the call. Don't worry. And don't spam like this. Okay. But I'm really happy that you got a good rank. They are very, very similar. And if you see this wave over here, if you say this wave over here, okay, like this, versus this wave, you will be like, ha sir, they are very similar. In fact, if I show them together also, they look very similar. But you start noticing the difference after some time. How? Look at it. Initially, do you see both their crests are together? Slowly, because their frequencies are not the same, that means the wavelengths are not the same, you can start seeing the crests do not actually merge together exactly after every oscillation. There is a gap between them. And that gap becomes more and more significant after 10-15 more waves, because every time one wave is completed, a small gap is created. Next wave, another more gap is created, and the gap keeps on increasing, and until the gap becomes so prominent that you see it actually looks like a destructive interference. Look at it. It is now a destructive interference. Are you able to see that, my dear students? After constructive, it just became destructive. Again, the gap keeps changing, and you will see again after some time they will merge on together and they become constructive. That is what happens when two or more waves of slightly different frequencies, very similar looking, meet or interfere each other. They will alternatively, constructively and destructively interfere with each other. That is what will happen. Okay, let's go back and let's change this frequency to maybe something like 9.2 and let's say 9.4 or something. You can see constructive, destructive, constructive. Okay, constructive, destructive, constructive. So what will happen to the resultant? Let's see what the resultant will look like. So let's put the resultant. Resultant is y is equal to y1 plus y2. Okay, let's have a look and see how their resultant looks like. The resultant is the blue one. Observe carefully. The resultant is the blue one. Wow, look at it. This is maximum, constructive, waxing, waning. Again, waxing, waning, loud sound, no sound, loud sound, no sound. So this is exactly the phenomena of beats. And you can see that right over here when constructive is happening. When constructive is happening, guys, just 1 second. When constructive is happening, observe this. Yes, the waves are in sync. And when destructive is happening over here, somewhere over here, observe this. They are, out of phase. Crest with trough, green crest, red trough. They are destructively interfering. That's where the sound is least. Exactly what we predicted over here. Is that okay? Everyone understood? Clear? What is the meaning of the phenomena of beats? You saw it visually. After this, you cannot probably have any doubt. Okay. So coming back to the point, in this resultant, from one maximum to the next maximum or one minimum to the next minimum, that is basically called as the beat period. Beat period. Capital T. And then you have something called as the beat frequency. Beat frequency, which is obviously 1 divided by the beat period. 1 divided by the beat period. The beat frequency, which is 1 divided by the beat period, this formula comes out to be, you take frequency of the first wave, take frequency of the second wave, but I don't know which one is bigger, so we put a modulus. That's it, the difference of the frequencies. That's it. So the beat frequency is simply put the difference of the frequency's positive value. Usually, remember this, a human ear can detect till 10 hertz to 15 hertz of beat frequency. Beyond that, it becomes very difficult for the human ear to detect it. So if the difference is more than 15 hertz, usually human ears can't distinguish it so easily. So till 10 to 15 hertz is what a human ear is capable of. Amazing. So, say for example, we do some questions on this. If two tuning forks is something which you would have used it in the lab. They are like a Y-shaped fork. You hit it on somebody's head or a surface, it will start vibrating, it starts producing a sound. On that tuning fork, there is a number written. That number represents the frequency which it produces. Two tuning forks of 400 and 408 hertz are sounded together. Their beat frequency is dash hertz. First thing, if some wax is added to the first, then the beat frequency dash increases, decreases. What do you think will happen? That's the question. The first answer is very simple. If these two frequencies are sounded together, then the beat frequency is just, like I said, the positive difference of the two frequencies. So it is just 400 minus 408 positive value, which is just 8 hertz. So the answer to the first question is 8. Very easy. Now what happens when you take that tuning fork of some frequency and you add some wax to it? If you add some wax to it, it will become slow. The oscillations, basically, the vibrations are going to become slower. That means the frequency will reduce. That means 400 might become 398 or it might become 397. So it might reduce to some lower value. So what will happen to the gap between 408 and 400? Earlier 408 and 400, the gap was 8. But 400 will become even less. That means their gap will widen. So that means their beat frequency will, what will happen to it? It will increase. It will basically increase. Is this clear, my dear students, why the beat frequency has increased? Absolutely. Yep. So that is what adding some wax to a tuning fork basically does. Okay, keep this in mind. So till now we have studied beats, we have studied basic interference. Okay, we will be, like I said, we'll be doing a lot of question practice in separate sessions. Obviously, there are question practice sessions which are coming up very soon. So be ready for that. Yeah, RNA series coming to an end. Probably this will be the last class or so. Okay, of RNA series. After this, just light waves and NCERT line by line, whatever some chapters are there, we'll complete that. After this is just problem solving, which is going to come. Okay, now the next thing is basically about standing waves. So we'll take a break and return and we'll start standing waves. Standing waves. Okay, so this is after the break. So we'll return after the break. Meanwhile, if you are new to the channel, like and subscribe. And maybe you are not new, you have still subscribed but forgot to like, subscribe. Yeah, make sure you smash the like button. All right, I'll return in a bit. Just give me 10-15 minutes and we'll be back. I hope I'm audible and visible to all of you. Welcome back, my dear students. It's time for standing waves, the last part of this lecture, and also a very important part. Okay. Yes, everyone, audible, perfect. Welcome, warrior, Pandus, whistle, Podoing, WP, hi Desha, hi Mardai, Adipati, welcome, Sanola, welcome back. Yes, let's go. So, what is this standing wave? Okay, you'll be like, sir, a wave which stands, a wave which does not move, is that a standing wave? Well, no. In general, what does a wave do? See, when you have a wave, it transports energy like a bus carrying passengers. A wave is like that bus which carries energy. Passengers are like that energy from one place to the other, like from one city or from one bus stop to the next bus stop. That's what a wave generally does. Such a wave is just called as a wave or a traveling wave because it travels from one place to other, like a bus carrying passengers from one place to the other. So it's a traveling bus, or we just say it's a bus. Okay. But what is a standing wave? A standing wave neither carries energy from one place to here or this place to here. It maintains the energy, contains that energy in that same place. It's like, you might have seen an escalator. An escalator. What does an escalator do? If a person is standing here, the escalator carries that person on the top. The person is like the energy, the escalator is like the wave carries the energy from the source to the destination. But imagine this person on the escalator is moving backwards, whereas the escalator is going like this. So the person is moving backwards, the escalator is going opposite way. The person will neither go on the top nor go below. So the person is staying there. This energy is contained. Energy is neither going up nor going down nor going right nor going left. So the energy is maintained. That means you need two things. You need a wave going one way and another wave going opposite way, and then what you will see is the net energy is neither going this way or that way, it is staying there. So that's exactly what happens in a standing wave. A standing wave is actually produced by the interference of two similar waves moving in the opposite direction. Moving in the opposite direction. Moving in the opposite direction. Thus, the energy is contained in a region. The energy is contained in a region and doesn't flow out of it, and doesn't flow out of it like a normal wave which goes from one point to the other. That is basically called as a standing wave. So for that you just need a wave like this and maybe another wave like this. So this is wave number one, and this is wave number two, going in the opposite directions. Two similar waves moving in opposite directions. What they produce eventually is basically a standing wave. You will see that they will produce something called as a standing wave. How does a standing wave look like? It looks something like this. Now I will explain this figure in a bit, don't worry. It looks like the structure of a DNA, RNA, right? So this is basically your standing wave. This is basically your standing wave. Don't worry, I will explain this to you. I'll explain this whole thing to you, don't worry. Cool? Crystal clear? Yes, sir. Done, sir. Perfect, sir. Okay. Now, like I said, I need two waves moving in the opposite direction. So, let's say our wave number 1 looks like this. A sine kx minus omega t, and this particular wave is going like this. You have another particular wave number 2 which is like this, which is A sine kx plus omega t. That means this is plus, so it is going in the other direction. So it will be maybe like this. When I use the minus sign, it is going towards the right side. When I use the plus sign, it is going to the left side. It's always opposite. That's what I had explained before also. So the resultant, therefore the resultant y will be just y1 plus y2, which means it is A sine kx minus omega t plus A sine kx plus omega t. Now when you add these two mathematically, okay, let's not get into the details, but what you get is this amazing equation. It looks like this: 2a sine kx into cos omega t. That's what I get. 2a sine kx into cos omega t. This is basically also called as the equation of a standing wave. This is also called as the equation of a standing wave. It is slightly different than the equation of a normal wave, where you have something x, something t, plus and minus. Here, it is something x, something t, but it is not plus or minus. Rather, the terms of sine and cos are multiplied with each other. So, that's how you distinguish between the equation of a standing wave versus the equation of a normal wave transporting energy from one place to the other. Very, very different. It is definitely not the same thing. This is what the equation is. Now let's understand this equation first of all. What the hell does this equation mean? Okay, and this standing wave equation, obviously, like I said before also, it looks like DNA structure. Okay, something like this. This is the standing wave equation. Now let's understand that particular equation. So when we look at the standing wave equation, this is your x, this is your y, oops, and I'll show it like this. Oops. Okay, sorry. Once more. And this continues. I'll explain everything, don't worry. I know you might be having a lot of questions in your head. What are these lines, sir? What are these curves? Everything I'll explain, don't worry. Okay, so this is basically how a standing wave looks like. Okay, now what is this? Let's understand. I just wrote down the standing wave equation like this. So let me write it down over here. Y, actually I'll put it over here. Y is equal to 2a sine kx into cos omega t. Instead of cos, you can also have sine. That's okay, no harm. And same way over here, instead of sine, you can also have cos over here. There is no harm in that. So sine, 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 cos, cos, sine, cos, cos, any combination will do. There is no hard and fast rule. Sir, you said over here sine kx and cos omega t. Sir, in the exam it came cos kx sine omega t. I was confused. Nothing doing. It is not going to matter at all. Sine replaced by cos, cos replaced by sine doesn't matter. Okay. In general, this is the equation. Now, what do these terms exactly mean? Omega, what is omega? Omega is the angular frequency of the waves which are interfering. What is k? K is decided by the wave's length 2 pi by lambda. So that's the angular wave number. Okay. What is A? A is the amplitude of the waves which are interfering. Now this wave, which is the standing wave which is produced, this standing wave, because it is produced by two waves of amplitude A, the maximum amplitude that you can get is 2A. The maximum amplitude that you can get is 2A. So technically speaking, this particular thing from here to here is nothing but 2A. From here to here is basically 2A. So the amplitude of a standing wave is how much? 2A. For once, forget the one which I have written in green. Just forget this which I have written in green. Just look at y is equal to something cos or sine omega t. This equation, doesn't it look to you like a simple harmonic motion? X is equal to a sine omega t, x is equal to a cos omega t. Omega is the frequency, it depends on time. So the y coordinate depends on, the time, at which time you are looking. So it keeps on oscillating, tuck, 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 up and down, up and down, up and down. This number outside decides the amplitude, that is how far it goes from the mean position on the either side, up or down. So think of it like this is equation of SHM, but this is the amplitude. So this whole term that you see over here is the amplitude of the simple harmonic motion, and the SHM term is this. This is the SHM, simple harmonic motion equation, or basically simple harmonic motion's dependence on time. So this is the oscillating term. So this is basically the oscillating term. This is the oscillating term which changes with time. With time it changes. But the funny part is the amplitude is not the same everywhere because it depends on x. The funny part is the amplitude is not the same for every SHM. Each line over here represents a SHM. Basically, think of it like this. The particle goes up and down, 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 like this. This is the amplitude. But as you go at different places, the amplitudes are not the same for every particle because this term only will be different. X changes. At this place, X is different. This place, X is different. X will keep changing. So the amplitude only is different. That's the reason why the amplitudes are different. So the extent till which it goes up and down is different. So this term, that's why I said, is the amplitude of the SHM. Krishna, nice to see you back. I was wondering where you were. Welcome back. I hope everything is fine. Is this clear? So the one term with x, whatever, sine, cos and 2a, the whole thing is called as the amplitude. The remaining term will be the oscillating term. This one will give me the exact location at any x value and at any time. Sir, at x equals to 3.2 meters, sir, at time is equal to 1.5 seconds. What is the value of y? At 1.6 seconds, this is the value of y. At 3.8 meters, this is what it is. This is where it is at this time. So at any x and any time, I can get this y coordinate. That is what it is. Okay. I hope this is absolutely clear. This is your standing wave equation. Okay. So this is amplitude, this is oscillating term, this is the exact location of that particular particle. Cool. Now, as you can see, not all the SHMs have the same amplitude. There are certain SHMs with a really good amplitude over here, and this particular SHM over here has a very good amplitude, maximum amplitude. This also has maximum amplitude. This also has maximum amplitude. This also has maximum amplitude. So the ones with maximum amplitude, means sine term or cos term will be 1. The maximum amplitude is basically 2a. Those points are basically called as antinodes. They are basically called antinodes. Antinode, maximum amplitude. But you will see this point, this point, this point, this point, this point, where sine term will be 0. 0 into anything is 0. So they are not moving at all. So the minimum amplitude obviously is going to be a big fat 0. And those points are going to be called as nodes. What are they going to be called as? Nodes. From one node to the other node, from one node to the other node, this particular thing is called as a lobe. It is called as a lobe or a loop. It is called as a lobe or a loop. From one node to the other node, not antinode to antinode, although the distance is same, but this is a lobe, this is half a lobe, complete lobe, lobe. This is not a lobe, although distance wise it is a lobe, but it is not called as a lobe. It is from a node to the next node. Yes. What is the significance of a node to node or a lobe in general? So whenever you consider a loop, one second. Whenever basically you don't worry, I will show you the simulation also in a bit. Yeah. Whenever you consider a lobe like this, lobe, or basically also called as a loop, which starts from one node to the other node, this distance, think about it, this would have been a wave. This would have been a complete wave. This is half a wavelength. So the lobe length is technically lambda by 2. This is lambda by 2. Is this clear? Why the lobe length is lambda by 2? Can you see a wavelength by 2? So technically over here, lambda by 2, lambda by 2, lambda by 2, lambda by 2. One wave, another wave. So whole thing is 2 lambda over here. Whole thing is 2 lambda over here. So the length of a lobe is basically lambda by 2. Now the significance of a lobe is that the energy of a standing wave is trapped between the two nodes, that is in the lobe. This is what our main definition was of standing waves. Remember, it is produced by the interference of 2 or more waves, and the energy is contained, trapped in a region and doesn't flow in and out. So what is that region? That region is called as the lobe. It will be trapped here. it will just be trapped inside, it will not be able to go anywhere else. That is what the significance of a lobe is. Is this absolutely clear? So you might see the kinetic energy and the potential energy is flowing within that particular lobe. Maybe the kinetic energy will come over here and maybe it will go like this over here. Maybe the kinetic energy will go like this, maybe it will go like this, and at the same time maybe the I don't know, maybe the potential energy will go like that, potential energy will go like this. So they are all just trapped within that particular lobe. They can't go anywhere outside. They're just trapped within that particular lobe. That's it. This is like the boundary. This is like the fence. It's like a jail. The energy is just inside. It can't go anywhere else. So that is basically how the energy is just flowing within this lobe, but not going from one lobe to the other lobe. That's one interesting thing. Another interesting thing about lobes and comparing it with traveling waves. Observe this carefully. Oops, slightly difficult trying. Okay, so this is standing wave, this is traveling wave. Observe this. Sometimes you might need the distinction between the two. So this is your normal wave, also called as the traveling wave. One of the major difference is the equation itself. Like the equation for this looks like this: a sine, you can have kx plus minus omega t. You can also have, instead of sine, you can also have cos. Here the equation looks something like this: y is equal to 2a. You can have sine or you can have cos. Here you will have kx. And then in 2, again you can have sine or you can have cos. And then you have omega t. One of the major differences is obviously the equation, number 1. Number 2, here you will see from the source, the energy flows. The energy will flow. Where will it flow? Where will it flow? Towards the destination. Towards the destination, or basically endlessly it will flow everywhere. So the energy is continuously flowing from one point to the other. Here the energy is trapped, like we saw. The energy is basically trapped and it cannot go anywhere inside or outside those nodes. Basically within that lobe it is trapped. So this is the node, this is another node. Between these two nodes it is trapped inside that particular lobe. That is the second major difference. Next major difference, here versus here. See, this particle has a small amplitude, more amplitude, maximum amplitude, and we saw that the particles with maximum amplitude are 2a, called as antinodes, minimum amplitude 0 are called as nodes. That means each particle has a different amplitude. But for a normal wave, maybe this particle has not moved till here or here, After some time it will move. Eventually all the particles go up and down by the same amplitude. So in a normal wave, right? So, right now maybe this particle was here. After some time it will come down, it will come down, it will come down, it will go up and down. So all the particles go up and down, up and down, up and down with the same amplitude. So here the particles have different amplitude. Particles have different amplitudes, and you can see that from the example of nodes and antinodes. Nodes and antinodes, of course. Here they all have the same amplitude. They all have the same amplitude. Very, very important. All of them have the same amplitude. Next major difference which you must know. Here between any 2 points on that wave, when one particle is here, other particle is here, after some time this will go up, this will go down. So there is a difference in the situation, means phase. The particles have phase difference. The particles have phase difference. We've seen that. Phase difference. And in fact, there was a formula also for it. Remember, delta phi is 2 pi by lambda into delta x. That was the formula. But here it is not like that. All the particles will go up together. All the particles will come down together. So all the particles will reach the extremes together, will cross the means together. That means they are in sync. But small catch, when in this lobe all the particles are going up, all the particles in the adjacent lobe are going down. So it's like all the particles here are going up, all the particles here are going down, they stop. All the particles are going down here, all the particles here are going up. So within the same lobe they are in phase, adjacent lobes are out of phase. That's the critical thing. So within the same lobe, they are in phase, whereas adjacent lobes, they are out of phase. And I will show this all to you, don't worry. These are the main differences between a normal traveling wave and a standing wave. The energy flow and the loop length, definition of amplitudes, maximum, minimum, nodes, antinodes, and the equation, of course, and where you get it from, and the main definition of standing wave. So that is what it is. Now let's have a look at these standing waves simulation so that you get an idea of it. Very, very nice simulations are there. Let me come back over here. How do you create a standing wave? You need two waves going in the opposite direction. Unfortunately guys, I can only create a wave from one side. I cannot create a wave from the other side. Can you suggest me some trick which I can use over here so that I can create a wave from the opposite side? Come on, my dear warriors. Think of some method so that I am able to generate two waves going in the opposite directions. Suggest me a trick, suggest me a way so that I can generate two waves going in the opposite direction. Only then I will be able to generate a standing wave. Is that right? Come on. Think about it. Think about it. What should I do? I can only create wave from one side. I just need another wave coming in from the other side. What do you think I should do? I should not do anything. Actually, think about it. It's already being taken care of. I'll tell you why. Shall I tell you why? It's already being taken care of. See what is there here. See what is there over here. There is a reflector. It's a fixed end. It's just going to reflect. So you generate a wave, leave it. After some time, it's anyways going to come back. You already have a wave coming back towards you. Just ensure that when the wave is coming back, you are also creating a wave. That's it. Isn't it? Correct, everyone? So let's do that. Let's do that and see what happens. So let's make it go up and down, up and down. Now the wave is going to reflect from there. It's coming back, and enough. Okay, I think it's like a almost standing wave, not the best standing wave, but let me just try to recreate it once more. Slightly better, not that great, but okay. Can you see these green particles right now are not moving much? What are those green particles approximately? I know they are not exact. They are like nodes. See, node, 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 node. Can you see that? Some particles are full of energy, jumping so much, antinodes. Some particles not so much, decently going up and down. Some particles are having more amplitude, some particles are having less amplitude. So this is basically a standing wave. Are you able to see that? The energy is trapped now between the two nodes. It is just going to go back and forth within these particles, but it is not going to jump from here to here. Whatever energy is trapped between the two nodes over here, it's just going to flow within these particles. Same thing over here, but none of them will go from one side to the other. That means the energy is neither going here nor going here. It's a trapped form of energy. That is a standing wave. Beautiful, isn't it? Clear? Now you will be like, sir, in this I am seeing one remarkable thing, sir. What is that? Wherever the ends are fixed, I am seeing a node. See this particle? A node, and the standing wave is formed accordingly. Oh, great. And I can also see all the particles inside a lobe are going up together and going down together, going up together, going down together. But particles in adjacent lobes out of phase. This is going down, this is going up, this is going up, this is going down. Up, down in the opposite manner in adjacent lobes. Exactly what I have written. Particles in adjacent lobes opposite in phase, in the same lobe. Whereas when you have a traveling wave, obviously all the particles will have a phase difference depending on how much they are separated by. Beautiful, amazing, sir. Now I saw that there are nodes at fixed ends. What if I make one of the end loose and then see what happens? Let's try it out. Let's just try it out. I'll generate a wave. Okay. I'll wait for it to come back. Oh, not the best wave. I'll generate it again. These are not very great waves, what I've generated over here. But yeah, somewhat. It's not really great. Oops, sorry guys. I'll do it once more. Somewhat okay, not the best. Do you see what is there over here at the loose end? It's an antinode. It's an antinode. So an antinode has been created now. But at the fixed end, do you see there is a node? Node, 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 and antinode. This is a half of a lobe. Node to antinode is a half a lobe. Node to node is a complete lobe. Half lobe has been created because of the free end relatively. So that's what a free or a loose end does on the string. So this is the manner in which you can create standing waves on a single string with a single source. You just have to generate a wave. And let it come back after some time. So now you have the reflected wave and the original wave going in two opposite directions. And now what you get is basically a standing wave. This is a standing wave. Is that clear, everyone? Yeah, awesome. So let's see the formulas for them. We have already seen these basic things over here. Great. All right. So a standing wave generated by reflection on a string instrument or an organ pipe. Whenever you do such things, if okay, your guitar, sitar, string instruments are actually based on the same concept, whatever I have just shown you over here. So your guitar, right, whenever you pluck the string of the guitar, it's actually waves are going back and forth and they are only creating those sounds. When you blow a flute or a trumpet, those pipe based instruments or organ mouth, so those are based on again standing waves concept, but for the reflection of sound waves. This is waves on a string. This is basically waves on a string. So guitar, sitar, or even piano, all those things have strings inside them and they are based on the standing waves which are produced by strings, waves on a string. But organ pipe instruments like trumpets, or maybe you're blowing a horn, or maybe you're blowing some flute, those are basically organ pipe instruments. They are again based on the reflection, but not of waves on a string, but waves of sound. Sound waves are longitudinal. These waves are transverse waves. So when I show a pipe based instrument, I might show something like this. I might show something like this. But remember, nothing actually is going up and down because it's not a transverse wave. It is just a representation of the pressure variations or the displacement of the particles in that longitudinal wave. So this is longitudinal in nature. Here you can actually physically see the things. So over here, you will definitely see a node, and here you will definitely see this one, which is nothing but a antinode. You will definitely see an antinode. Here you will again, for a closed pipe, imagine you have a pipe, you close that side, that is a closed side of the pipe, that will be definitely a node, that will definitely be a node, and here you will obviously you will definitely get antinode. Antinode on the other side. So this is what it looks like for pipes which are longitudinal. These are transverse waves. Please do not confuse between the two. So this is for transverse waves. Whatever we are drawing over here is basically longitudinal waves. Longitudinal waves. Basically, example, this is sound. Here you can think of the example for the wave on a string. Wave on basically a string. String instruments. So all the string instruments like guitar, etc., they are based on this principle. Sound-based instruments like flute, etc., they are based on this concept. But the formulas are very, very identical. Okay, so it's just instead of closed pipe, this is fixed end. This is antinode, which is free. So this is like a open side of the pipe. Is this part very, very clear till this point? Shall we go ahead? Much better, Krishna? Yeah. And I realized where the problem was. The problem was in the AC of my room, because obviously I have to use AC. Without AC, I can't survive over here because this board generates a lot of heat, and if it is not cooled down, the board gets stuck. There are many lights here, camera, laptops, mics, and so many other things, electrical instruments. So they generate a lot of heat, plus my body is also heated up. The room is closed, it becomes humid, so you need the AC. But I have, unfortunately, for some reason, I had not cleaned the AC. There was a lot of dust. So I guess there was some fungus, some bacteria inside that AC. I have to get it cleaned also. So I think that was the reason. And that's what I think doctors need to do eventually. So, you know, my doctor also was very surprised why I have given you the correct prescription. I have given you the correct medicine and the dosage. By now, it should have been cured. There is something else which is bothering. The blood test report also came in fine. And maybe in the near future, you might also encounter such patients like me. And the doctor was also surprised. By now, you should have been cured. You generally don't fall ill unless you have something major. So then I thought about it. And then I realized, I noticed a pattern. Every time I take a class, I was falling sick. So then I thought maybe it must be the AC. So I opened up the AC and I saw, my goodness, it was crazy. And then I think my doctor felt very happy. Like, okay, so nothing wrong with my medicine, something wrong with your room, maybe your whole ambience. So this is how you have to diagnose, guys. I mean, in the future, as great doctors, the cause might be from somewhere else. You might be thinking in one thing, but something else might be triggering. You might have to look at some patterns. You might have to see some variations, and you might have to compare some different people or different time zones or different things. You have to see what is affecting what, and maybe that's when you will get the proper diagnosis. Is that right? Correct. Okay, so let's see the three different possibilities in this. There are only three different possibilities which you can have for these kind of stuff. What are the three different possibilities? Let's have a look. Okay, the first thing is where both sides are basically closed. Basically, both sides are fixed. Both sides are fixed. This is one possibility. And when such a possibility occurs, then you will have a standing wave probably like this with nodes on the both ends, with nodes on both the sides. Node over here, and you will also have node over here. This is one possibility. The second kind of possibility which you can have, like you all can guess, like this. This is free. This is fixed end. This is like the closed side. This is like the open side. So on the open side, you can probably have antinode. The closed side will definitely have a node. This will be again antinode. And this side you will have a node, like we all saw some time back. Yeah, so this is Another possibility of a standing wave creation, both sides fixed or closed, one side fixed, one side free, one side closed, one side open. And obviously, what is the third possibility, my dear students? Both sides should be free, right? So that is the last possibility that you can have. Like this. So this is also open, this is also open, this is free, this is also free. So free sides always will have antinode, and something like this maybe. Yeah, this is the kind of standing waves that you can get in all the three cases. Is this clear? Okay, cool. These are the three possibilities. One thing though about pipes, there is one small catch when you are talking about the description of pipes, and let me mention that as well. Whenever, especially you are talking about open side of the pipe, whenever you are talking about the open side of the pipe, my goodness, whenever you are talking about the open side of the pipe, usually you will see that the antinode is not exactly formed over there, it is formed slightly outside actually. This is what has been practically observed. So the antinode is slightly formed outside over here, something like this. And this is where exactly you get the antinode. You were expecting the antinode to be formed here, but it is formed slightly outside. So there is some small correction which you need to do. That is also called as end correction. That is also called as end correction. So whenever you are measuring the length of the pipe, you have to consider some extra length because the antinode is not exactly formed here. So there is a small correction to it. That E is basically 0.3 times the diameter of the pipe. The diameter of the pipe. So whatever is the diameter, based on that, the end correction might be more or less. If more diameter, more end correction. Small diameter, less end correction. So that's how the antinode slightly shifts on the outer side only for the open pipe. Closed pipe or loose end, fixed end, no correction. The correction is only over here. That's why I'll put a star mark. That's why I'll put a star mark only over here, because I put it on the next slide. The end correction needs to be taken into account in certain cases. 0.3 times of D. Okay, so that will add to the length of the pipe. So all the three modes are done. Now you will be like, okay, sir, what are the formulas? Let's see. First of all, let me tell you, on a string or on a pipe of certain length, it's not necessary you might have these many lobes. The main condition is you should have two nodes. So what are the different possibilities for a given length? Let's try to understand that. Let's try to understand that. Okay, my length is this much. The main condition is there should be two nodes. The smallest frequency which I can have, or the largest wavelength which I can have, is this. Below this I can't go because at least I should have two nodes. These are the least number of nodes that I can have for a string which is fixed on both sides or a pipe which is closed on both sides. This is the first possibility. Second possibility is you introduce one more node like this. Now there are two lobes. This is also okay. Still you have two nodes on the end. One more possibility is also there like this. Check this out. Now you have three lobes and you can see again two nodes are there at the ends. In general, if you continue like this, what happens? What happens is basically, my dear students, you should essentially get like this. N number of lobes. This is 1. This is n number of lobes. Here there were 3 loops, 2 loops, a single loop. In general, you should get n number of loops over here. Are you able to see that? Yes, but the length is constant. So, can I say that the length, all right, the length which is there is nothing but n times of the length of a lobe, n times the length of a lobe, basically lobe, n number of times. What is the length of any lobe? It is lambda by 2. This is just n, guys, and the total length which you have is basically L over here. So I'll just put L like this. But wait a minute, don't I know the formula for lambda? Definitely I know the formula for lambda. V is equal to F lambda. Lambda is equal to V by F. Lambda is equal to V by F. So therefore the frequency will be NV by 2 times of the length. NV by 2 times of length. So this is in general the frequency of the wave which is moving back and forth. So this is a very, very obviously important formula which we have got. This is a very, very important formula which we have got. Is this clear, my dear warriors? NV by 2L. The same analysis you can also do. The same analysis you can also do for a fixed free end. For a fixed free end, and let's see what are the different possibilities that you can get. Given that the length is fixed, I can't change the length. On that same string or on that same pipe, what are the different possibilities I can do? A node and an antinode. The smallest possibility, the least possibility is this, a single node and a single antinode. Next, maybe something like this. Node, antinode. Oh, this is also fine. Okay, maybe even this is also fine. Perfect. Node, antinode. So from this I can see that I should always start with maybe a node, and I will continue like this, and I will always end with half a lobe over here. That's what I can see. One and a half, sorry, this is half, this is 1.5, 3.5, 4.5, 5.5. Basically, that is what I can see. Half, 1.5, 0.5, 1.5, 2.5, 3.5, 4.5, like that. So it is always, I will see that the length will be something 0.5. Now anything 0.5, can I say it is odd number by 2? Check it out. 2.5, 5 by 2. 3.5, 7 by 2. Anything you take, 0.5, 1 by 2. 1 is odd number. 1 by 2, 3 by 2, 5 by 2, 7 by 2, 9 by 2, 11 by 2. All these are 0.5 numbers. 0.5, 1.5, 2.5, 3.5. Everything is odd number by 2. Yes or no? Any odd number, 13 by 2, what is it? 6.5. Correct. So all these are basically, I can say, these are nothing but odd numbers by 2, and you will just write over here, number of lobes into the lobe length, and the length of a lobe is lambda by 2 over here. So this is odd number by 2 is equal to your length. But wait a minute, But wait a minute, lambda is V by F. So what we can do, I just write odd number, 2 2s are 4. This is V by F. Therefore, the frequency is odd times V divided by 4 times of the length. So there is a small change in the formula, like you can see, my dear students. Instead of NV by 2L, instead of NV by 2L, it is odd V by 4L. 4 instead of 2, and instead of N, it is odd. N was any number, 1, 2, 3, 4, 5. Here it is only odd. So 1, 3, 5, 7 only. Correct. Very good. So this is for fixed free or closed open side. Similar analysis if one does over here for both sides free or both sides open. Let's see what exactly happens over here. Okay. You should have antinodes at the end. The least possibility you can get is just this, a single node but two antinodes. A single node but two antinodes. The next possibility that you can probably get is this, I believe. Just check this out. Yep, perfect. An antinode, two nodes and an antinode. Yes. Next possibility that I can get is probably this. Just check this out. Oh, nice. Perfect. So in general, towards the end, I should have half lobes with antinodes. This will continue. And the same thing on the other side. Yeah, this is what should happen. If you notice, this is half plus half, one lobe. Half plus 1 plus half is 2 lobes. Half plus 1 plus 1 plus half, 3. So, 1 lobe lengthwise, 2 lobes, 3 lobes, 4 lobes. In general, can I say the length is just n times, because the two halves become 1. So, it is in general total integer, n times the length of a lobe, Wait a minute. I saw this same number, same expression here also. Length is n times the length of a lobe. Oh, it is for a fixed, closed side. Okay. So hence the formula is the same. So frequency will be NV by 2 times of the length, where this is obviously the length. Same thing over here also. This was the length. Is this clear? So this one, both sides free or both sides fixed, have the same formula. NV by 2L, you can see NV by 2L. Same formula is there even over here. There is no change. The only difference is where both sides are different, fixed free, free fixed, closed open, open closed, then it becomes odd V by 4L. Otherwise, there is no difference. Is this clear, everyone? Absolutely? Okay. Fair enough. Now, let me tell you one important thing. If you look at the frequencies for fixed end, how will the frequencies look like? When n is equal to 1, the first frequency that you get is just V by 2L. When n is equal to 2, the next frequency that you get is 2 times V by 2L, which is 2 times of F1. When n is equal to 3, the next frequency that you get is 3 times V by 2L. V by 2L is F1. So it is 3 times of F1. So same thing continued for any nth thing. The Fnth becomes n times the first frequency. N times the very first frequency that you get. It's all in integral multiples. Same logic I can also apply over here when both sides are free. When n is equal to 1, the first frequency that you get is V by 2L. When n is equal to 2, F2 will be, 2 times V by 2L, and so on and so forth. So, obviously n is equal to 3, F3 will be, this was 2 times F1, this will be 3 times F1, So for any n, Fn will be n times of F1, n times of F1. So all integral multiples are there, 1 times F1, 2 times F1, 3 times F1, 4 times F1 for free. What about odd? What about odd one? Let's try it out. The first odd number that you can get is 1. So the first frequency that you get is odd number is 1. So V by 4L. V by 4L. The next odd number that you can get is 3. So the next frequency that you get is basically odd number is 3. 3V by 4L. So I will not call it typically F2. I will call it F3 because the number I have put is 3. So typically this is 3 times of F1. The next odd number that I can put is 5. So I will get 5 and this is 5 times of V by 4L. V by 4L was F1, so it is 5 times of F1. In general, for any odd number that I put, the F oddth frequency is that odd times of the first frequency that I put. Odd times the first frequency that I got. So all frequencies are not there. 1 times F1, 3 times F1, 5 times F1, 7 times F1, 9 times F1, 11 times F1, odd times F1. Certain multiples of the first frequency only are present. Now, what are these numbering schemes called? They are called harmonics and overtones. Let's understand what is the meaning of a harmonic and an overtone. So remember, the least frequency is called fundamental. Least frequency is basically called fundamental frequency. Next, harmonic is how, or basically the multiple of the fundamental. Multiple is the multiple, harmonic is the multiple of the fundamental. Is the multiple of the fundamental. And the last one, you have something called as the overtone, is the number, is the serial number, I would say, is the serial number above the fundamental. You will see these terms very, very often. Overtone, harmonic, fundamental. Let's have a look at it. Yeah, Krishna will be having it very soon. I know the next chapter is light waves. I was planning to do it today, but then I realized I think we should do interference, phase difference, everything first, because then light waves will become difficult if you don't do it. So that's the reason why I kept this class instead of the light waves. After this, light waves will become a very, very easy thing. So what do I mean by this? Observe this. Let's say there is some instrument in which these are the frequencies: 10 Hertz, 20 Hertz, 30 Hertz, 50 Hertz, 90 Hertz, 100 Hertz. These are the frequencies. Which is the lowest in them? Which is the lowest least frequency? That is called as fundamental, right? So the fundamental over here is basically this one. So this is basically your fundamental. This is basically your fundamental frequency, which is basically 10 Hertz. Okay. Harmonic is the multiple of the fundamental. 10 is which multiple of 10? Fundamentals, which multiple is 10? First multiple. 10 into 1 is 10. So that is why I will call 10 as the first harmonic. First harmonic. Because you have to multiply 10 with 1 to get 10. To get 20, how many times will you multiply the fundamental, which is 10? 2 times. 10 multiplied by 2 is 20. So that is why this is called second harmonic. Second harmonic. 30 you will get multiplying 10 how many times? 3 times. So that is why this is the third harmonic. 50 you will get it by multiplying 5 times, so fifth harmonic. 90 you will get it multiplying it 9 times, so ninth harmonic. 100 you will get it multiplying 10 times, so 10th harmonic. Is this clear? What is harmonic? How many times do you need to multiply the fundamental to get that particular frequency? That is what harmonic is, the multiple. Overtone is the serial number above the fundamental. Check this out. Above the fundamental. Over means above, over and above. Okay, let's understand it. 10th is already the fundamental, don't worry about it. 20, serially, it is the first number that you get after 10, which is the fundamental. After, over. So that is why this is called as the first overtone. Serially, if you mark it 1, 2, 3 like that, that's what it is. This is nothing but the second overtone. Serially, this is third overtone. This is fourth overtone. This is basically fifth overtone. Got it? Serially, you will go it. That's it. That is what is the meaning of overtone. Don't worry, I'll give you one more example. Okay? So learn from that example now. Don't miss this example. All right? Let's learn from another example as well. Yep. Let's learn from another example. Let's say it is 5, 15, 25, 40, 45, 50. Come on, who is the least frequency among them? The least frequency will always be what? Fundamental. So who is the fundamental frequency? Obviously, I hope you can see 5 automatically becomes the fundamental frequency. Okay. So now, if you notice, multiple wise, 5 multiplied by 1 gives me this number 5. So hence, this is first harmonic. 15, how do you get 15 guys? By taking 5 and multiplying it 3 times. So this is third harmonic. 25, how do you get it from 5? 25, how do you get it from 5? 25 is 5 times of 5. So this is fifth harmonic. 40, how do you get 40 guys? You get 5 multiplied 8 times, right? So that is why this is the 8th harmonic. Always fundamental into how much is that number. 45, how do you get? 5 into 9. So this is 9th harmonic. And 50, how do you get, my dear students? 5 multiplied by 10. So this is 10th harmonic. Got it? Understood? Clear? Absolutely. But overtone wise, go serially, exclude the fundamental. What does the definition say? Serial number above the fundamental. So above, that means don't go literally, above means like that. Above means number wise. After 5 comes 6, 7, 8, 9, 10 like that, 15. So this is serially, this is 1. So this is first overtone. Serial number, second overtone. Serially, third overtone. Serially, fourth overtone. Don't even worry what this number is. Serially you will do. So this is fifth overtone. Is this clear? Absolutely, my dear students. Okay. So now think and tell me, over here, who is the fundamental? This is the fundamental frequency. This is the least frequency. So this becomes fundamental. This will become fundamental. After fundamental, you will get first overtone. Then you will get the second overtone and so on and so forth, right? Second overtone, third overtone, fourth overtone, etc. But harmonic wise, this is the first multiple. So this is first harmonic. First harmonic. Then this is 2 times the fundamental. So this is second harmonic. Then next you have the third harmonic. and then you basically get the nth harmonic. Nth harmonic. So here, if it is the nth harmonic, this will just become the n minus 1th overtone. N minus 1th overtone. N minus 1th overtone. Correct? 3, 2, 2, 1. N minus 1. That is how it will go. Clear? Same way. I'm so glad, Chandan. Everything is made easy for you, thanks to me. And the same way, if I go over here, free, open side, it's the same formula, right? NV by 2L, so nothing will change. So this will then become the fundamental, the least one, V by 2L. Okay, so this will become the first overtone. This will become the second overtone, and so on and so forth. Same way over here, harmonic wise, this will be the first harmonic. This will become the second harmonic, because 2 times. This is 3 times the fundamental. So that's why the third harmonic. How many times the fundamental? 3 times. This is 2 times, like that. Now, only difference is for this guy. When you fix and free it, close and open it, that's when the difference comes. That's when the difference comes. Yep. So obviously this is again the fundamental. This is again the fundamental. This is serially first overtone. Then this is the second overtone, and so on and so forth. Here, this is obviously the first harmonic, because the fundamental is always the first harmonic. So first harmonic. What is this? 3 times the fundamental. So third harmonic. So only odd harmonics are there. 5 times. So this is the 5th harmonic. So only odd harmonics are there. Only odd harmonics. Only odd harmonics are there, not even harmonics. Is this clear, everyone? How this works for standing waves? So a lot of people have a lot of confusion in this. So I hope I have made things absolutely clear on this. Now there are 2 instruments which you should know regarding the standing waves. One is called as the sonometer. A sonometer basically produces standing waves on a string. This is the first instrument. And the second instrument that you should know is a resonance tube. This produces standing waves with sound, which is longitudinal in nature. So this is longitudinal, this is on a string, that means transverse. The setup is very easy, you should know this setup, not that difficult at all. You have a table and you need a string, which is, you need a string obviously, which is attached on one side, and you obviously need to give some tension in the string, only then the waves will pass. So to provide the tension, you need to suspend a weight, something like this. K This is a setup, guys. Basically, you connect the string to one side, attach it. You have two wedges, and then you have a pulley which suspends that weight via that string. And that weight produces the tension. Only when there is tension, wave on a string can travel. Remember that? And the wave speed is given by what is the formula for V? It is root of tension by mu. The tension over here is given by mg. The tension over here is given by the weight which is attached to that particular string. Okay. Now, if you take a tuning fork, something like this, and you make it vibrate, okay, it vibrates, it has some frequency f. Those vibrations from the tuning fork will travel through the table, through the wedge to the string will start vibrating, it will generate a wave, it will reflect back from here, and it will produce a standing wave. When a clear-cut standing wave is produced, only then you can count the lobes, because both the sides should have fixed end, else you will not see a steady pattern, it will look very weird. When you see a proper loop system formed with the nodes at the end, that's when you will stop adjusting the length between them. And that's when you will measure the length, measure the number of lobes, and you will use our standard formula for frequency. What's the formula for our frequency? It was nothing but n times V by 2 times of the length. And the V over here is this V. So therefore, you will see that the frequency will be nothing but n by 2, and the length which you will measure, and the velocity will be root of mg by mu. Now this, either you can use it to find the unknown mass, or you can use it to find the unknown frequency of the tuning fork. Usually it is used to find the unknown frequency. You will know the mass which you are attached, you will know the acceleration due to gravity, you will be knowing the string characteristic, how much mass is there per unit length, the number of lobes you can see through the naked eye and note it down, length you can use a meter scale and measure it, and this frequency of the unknown fork you can measure it. So you substitute all the values and measure it, and then see what is the actual number measured here in the actual number mentioned on the fork, and you will see the difference, and you will be like, okay, there is some 2-3 hertz difference, that's a marginal error, it's acceptable, and if you are very close in the limits, you will be given full marks in the actual practical examination. So that is how this setup works. Oops, thank you for reminding me. Yep, thank you for reminding me. Is this clear, the sonometer setup? Okay. The next one is called, like I said, resonance tube. So I'll tell you what happens here. You need water in this setup, and there is a tube which is actually dipped inside this particular water, and I'll tell you why you need water in a bit. Hold on. And because this is longitudinal waves, that's why you need a pipe, not a string. Sonometer was used to determine the unknown frequency of the tuning fork. Usually you will see this setup is used to determine the unknown speed of the sound which is in the air. So what you do is, first take a pipe which is open on both sides and completely immerse it inside that liquid. Completely immerse it inside that particular liquid. Okay, and slowly take it out. And when you are doing that, there is one important job of a tuning fork which is placed over here like this. This tuning fork will obviously be made to vibrate. It will have some frequency F. This is that tuning fork. Just like over here. Okay, what happens is it generates sound, because when you hit something, it will start vibrating. It will vibrate the particles of air around it. So that will produce sound. You can hear that sound very easily. And that sound will travel in the pipe, but there is a water surface. Why water was used? Why that liquid was used? The job now it will be very, very clear. This liquid is used to reflect the sound. What will happen is whatever sound will come over here, it will get reflected. This side will actually act like a closed end. Yes, this internally acts like a closed end. Acts like closed end. And the upper one over here is like the open end. Now what happens is there is a standing wave produced, and slowly when you take it out, the first standing wave which will be produced will be the first harmonic, and this is how the standing wave will be. This is the first wave that will be produced, or you can do it at any instant. I mean, you can keep pulling it and you will suddenly hear a loud sound. When you hear the loud sound, that means it is resonating. That's why it is also called as resonance tube. And when you hear that loud sound near the tube, then you will stop. You will stop doing anything, because now you are hearing a loud sound, and you will actually end up measuring what is the length of the tube which is outside. And let's say I call it as L1. L1. There could be some small end correction also involved over here, and that can be measured by measuring the diameter of the tube. Remember that the end correction will be always 0.3 times of d. So the diameter of the tube, if it is known, so L1 plus that E will give me the total length of this standing wave which has been produced. Now what you do is, if you write the formula over here, that frequency will be nothing but n, whatever is that n, okay, V, I don't know what that V is, okay, which we have to find, by 2 times of L, but don't write L as L, you will have to write L plus that E, that end correction has to be counted. Oh, sorry, it is not the number 2, it will be the number 4, because this is fixed free, open closed. So odd V by 4L, it is not even N, it will be basically odd number, some odd number, V by 4L. L over here will be L plus E. Got it, everyone? This is the formula that anybody will use. But there is a problem. I know the frequency of the tuning fork, I know the length, I know E, but I just don't know odd number. If I know the odd number, my job is done. I can easily figure out what is the speed of the sound. So what they usually do in such problems is that instead of this equation, see, if you know all these things, use this, no issues. Usually what you will do, you will say that L1 plus that end correction, will be some odd number times lambda by odd number by, what is it, half a lobe, right? Half a lobe. So lambda by 2's, yeah, like this. Remember, that was the general equation which we wrote over here for fixed free end. Where is it? Yeah. Total length will be odd by 2 into lobe length, odd by 2 into lambda by 2. This is what you do for fixed free or open closed end. Here the length will be the effective length, which is actual length plus that end correction. That is what I will write over here. Imagine now I pull it out once more to again hear the resonance after some time. I'll just pull it out slightly like this. And what I notice is sorry. I notice another standing wave formed like this. This time, this is that second length which I get, the next consecutive length. Obviously, there is the same amount of end correction also which is involved. So the next time when I hear the next loud sound, means resonance is occurring, standing wave has been beautifully produced. Next time it will be L2 plus that same end correction, but this time there is a small catch. It will be the next odd number by 2 into lambda by 2. Not any odd number, the immediately next odd number. Is that right? The immediately next odd number. Now I can see a beautiful mathematical thing which I can do over here. I will subtract the 2. Guys. That's all I'm going to do. So what I will get is L2 minus L1. Obviously, E and E will get cancelled. E minus E, definitely it will just get cancelled, right? So don't even worry about it. Okay, plus E minus E, obviously getting cancelled, is equal to, notice this, lambda by 4, next odd number minus that previous odd number. Okay, let's leave it. So L2 minus L1 is equal to lambda by 4. What is next odd number minus the previous odd number? 11 minus 9, 2. 13 minus 11, 2. 25 minus 23. Odd number, next odd number, 2. Always this number is going to be the number 2. Oh, wow. L2 minus L1, lambda is V by F. F is the unknown frequency of the tuning fork. V, I don't know, I have to find it out. Okay, and 2 and 4 cancels and I will have just the number 2. So therefore, V will become 2F into L2 minus L1, where F is the frequency of the tuning fork, and you can either determine the unknown frequency if you know the speed of sound, or if you know the frequency, you can determine the speed of sound. So here, this V is nothing but the speed of sound which has been determined. Speed of sound. The speed of sound. Is this absolutely clear, my dear students, how we did this? So it's a beautiful derivation, as you can see. So if you understand it peacefully, clearly, then you will never face any problem. Or else you'll be like, why did this formula come? What have they done in the textbook? Textbook will always confuse you. That's why you always need a mentor, you need a teacher, you need a guide, and that's why I'm here. So that's how you do this resonance tube. So we have done the complete theory of standing waves, by the way. I will be doing problems, like I said, in a separate class. And if you have understood everything, I mean, like really, you should appreciate me in the comment section by putting up anything. Like you can just put a simple heart also. You can just say, yes, sir, loved it, sir, done, sir. So this is, yeah, the last session of, I think, RNA. After this, we are going to see thermo and fluids I have already done in a Super 6 series. You can watch those old classes also. We'll be doing mainly problems. Plus in DNA batch, I am already done thermos And the fluids, it's done in the DNA batch. DNA batch is our batch where the entire syllabus has been covered beautifully, and now the revision phase is going to start. And obviously test series, books, everything is a part of it. So if you have not yet been a part of it, make sure you're a part of it and complete your syllabus. Okay, but most of the syllabus, has been done in the RNA, and NCERT line by line is taking care of your 12th standard syllabus, so you have nothing to worry about as such. Cool. Have a great time, guys. I'll be seeing you again, and do not forget to like this video, share this video with your friends, and obviously subscribe to the #1 NEET English channel in the country, Vedantu NEET English. Thank you so much. Have a lovely day ahead. See you again very soon. Take care. Bye bye. See you in the comments.